All right, so welcome everyone from CNMI Guam and American Samoa to session 15 in our wastewater operator training series. Today is part one of disinfection. We're going to be focusing on effluent disinfection. We'll talk about chlorination, dechlorination, and some very related and important safety issues. And then in 2 weeks, AJ is going to pick up where we left off and cover UV and other disinfection methods. Regardless of the kind of disinfection you may use in the facility that you currently work in. As an operator, you're going to be responsible for understanding the basics for pretty much every kind of disinfection that is typically used out there in the world. So I'm going to turn my camera off here just because I find it distracting, and we'll get into our little introductions here. I'm James Markham again, a research engineer here at Southwest EFC, and with me is Valeria Cortez Mora, who's running the back end, monitoring chat and making sure we stay on task and on time. Again, funding is provided by the EPA. We're from the Southwest EFC. I'm sure we've gone through this enough times to know, keep yourself muted during the session. Unless you have a specific question to ask, there's a small enough group of us here. I think it's okay to unmute and ask. But you can always use the chat feature to ask any questions as we go along if there's anything that you don't understand or would like further elaboration on. And then when we have a Q&A session at the end, so Valeria will kind of monitor the chat and determine whether it makes sense to break in now or hold a question that's been asked until the end. We'll do our best to answer them. If we can't, we will get back to you. Of course, the series is designed to supplement and reinforce the ABC Need to Know criteria for the wastewater operator 1 and 2 exams. Throughout the series, there's going to be some higher level topics covered, but we don't always follow the order that's listed in the need to knows. But the whole goal here is to, again, sort of get you familiar with these topics and make you confident operators. That being said, this video series, again, is not going to be enough to get you through the exam by itself. Use all of your resources that are available. These two, that's a shot of my desk from a couple of days ago. These two guides are really, really useful. They're kind of the Bible when it comes to wastewater treatment, and a lot of the information in this series comes from these books. So if you have copies of these, I would advise using them with great frequency. As I said, we're in session 15 of 26. We're right here, disinfection part 1. That should say safety, not related math. We're not actually going to do any math today. All of the prior sessions, including the water series track, are online. I checked on that earlier today. This particular session, the recording and the slides should be up within a day or two. And last but not least, if you're attending in a group session, make sure you sign your group attendance sheet. The facilitator is going to forward those to us to keep track of your attendance so that you get credit for the hours that you're with us. So with that, let's get into today's content. We're basically going to be doing an overview of disinfection. We'll talk about some of the chemicals that are used for disinfection. We'll talk about factors that affect disinfection. We'll focus primarily, again, on chlorination today. We'll talk about dechlorination, really important step. We'll go over some basics of chlorination and dechlorination systems, and then we'll wind out our session today with a talk about safety. So I've got a poll question for you to start things off with, just to kind of get a sense of what you're familiar with, which is, what form of disinfection does the facility that you're currently working at use? Do you use sodium hypochlorite, which is going to be the liquid form, either purchased or self-generated? Do you use calcium hypochlorite? Do you use chlorine gas? UV disinfection, some other method, or you're not sure? So Valeria, if you wouldn't mind firing up that question. And again, there's no wrong answers here. And I guess if you're in a group session, you can just sort of take a poll and see what you're familiar with. Okay, we'll give this another 15, 20 seconds. You can always put not sure. All right, Valeria, why don't you just go ahead and end that poll? All right, so you can kind of see we use a variety of methods, but sodium hypochlorite and calcium hypochlorite seem to be the most common out there, with some folks who use something else or maybe don't disinfect or aren't sure. All right, so let's talk about um, what disinfection is. So the idea here is that we're using chemical or physical processes to inactivate harmful microscopic organisms so that they can no longer carry out their cellular processes. Notice I didn't say necessarily kill them, although some of them are killed. The main goal here is to make sure that they can't actually make us sick. They can no longer carry out their cellular functions. They can't reproduce, and that they're not harmful to the environment or to organisms that consume the water, like animals and us. We do that by using chemicals to either alter enzymes or damage the DNA or RNA of those microbes, but we're not necessarily killing them. That's okay as long as they're inert. We're safe, and we do this because microscopic organisms pose a threat to the environment and to other humans. And that list on the right-hand side is a short but exclusive list of the kinds of infectious agents that are potentially present in untreated domestic wastewater. A lot of those things will probably be familiar to you, even if you don't necessarily know the scientific name of the organism. The diseases will be familiar: typhoid fever, cholera, giardiasis, gastroenteritis, infectious hepatitis. These are all things that used to kill people on the regular before wastewater treatment was kind of the norm. The big five that you kind of have to pay attention to are cholera, dysentery, polio, typhoid, and hepatitis. But those are potentially in wastewater. They're transmitted, through our bodies, through the waste that we excrete. So we want to make sure that we either take them out of the stream, or at least, if we can't take them out, inactivate them so that they can't continue to make us sick. So one of the reasons we do it is basically to keep ourselves safe. The other reason we do it is because we have to. It's typically a requirement. The Clean Water Act permits. So Clean Water Act passed in 1972 basically requires that wastewater be disinfected before it gets discharged into bodies of water categorized as waters of the United States. It's kind of a technical term that changes a little bit once in a while, but basically it's any lake or river or navigable water and the tributaries there too. So if you've got a wastewater treatment plant that has to discharge in one of those, you typically have to have an NPDES permit, so National Pollutant Discharge Elimination System permit. Those are going to be issued by the EPA or the state, depending on where you're at and who's got primacy. So we do it to keep ourselves safe. We do it because the law says we have to. So let's talk about the things that we actually use for disinfection. Chlorine, chlorine dioxide, chloramines, bromine, ozone, all of these are potentially used for disinfection of wastewater. And they're basically used because they're oxidants. Chlorine is really kind of the most common one that we use out in the field. And the three types of chlorine that people were sort of checking off on our list earlier are sort of the three most typical types that Jeffrey, can you mute yourself, please? Thank you. Chlorine comes in three different forms typically where it's used in wastewater treatment plants. So first is chlorine gas. I noticed nobody checked that in our group, but it is one of those things that shows up on the exam with regularity. So you need to know about it. It's 100% chlorine. It comes in compressed form, where it's liquid, basically in containers like the ones you see there on the right. Those are 150-pound cylinders. They come in 150-pound cylinders, and then 1-ton cylinders. Those cylinders there are about 53 inches tall. The 1-ton cylinders, 8 feet long, 3 feet in diameter. The bigger ones are used typically by medium to large municipal systems. A ton of chlorine is a lot. Even 150 pounds is a lot, and it's under pressure. And if you think about the fact that chlorine gas expands when it's released out of a liquid form to about 460 times the volume it occupies as a liquid, you can see why safety is really, really paramount. And these things are typically, chained to the walls. There's lots of signs around and lots of safety measures and SOPs around them to ensure that accidents don't happen. We'll discuss a little bit more about this in the last section about safety, but it's really important to recognize that this stuff can kill you, and there are a lot of safety precautions around it that should be followed all the time without exception. There's also sodium hypochlorite, which is effectively bleach. Household bleach is sodium hypochlorite at a sort of 5 to 8% ratio or concentration. The stuff that's used for wastewater treatment is typically a little bit stronger in the 10 to 12.5% chlorine. It's typically mixed by a manufacturer, comes to you pre-made, has a shelf life of anywhere from 1 to 3 months, depending on storage conditions. And then there's the solid form, which is calcium hypochlorite, also known as pool shock. It's about 70% chlorine, roughly, typically mixed on site by operators who are trained to do so to a 1 to 3% solution. Has a slightly longer shelf life of about a year. In terms of sort of safety issues and dangerousness, sodium hypochlorite is the sort of least dangerous and has the least issues. Gas is the worst, and calcium hypochlorite sits sort of in the middle. Sodium hypochlorite, the bleach, can also be generated on site. Some places do this because basically all it is salt and water and energy. So the picture there on the right is an on-site electrolysis chamber where they're basically using sodium chlorine, table salt, sodium chloride, excuse me, and an electrolysis chamber using that to generate bleach essentially at a sort of 0.4 to 0.8 parts per million strength. So weaker than the stuff that you normally buy, but under certain conditions, this is a cost-effective and useful way of doing this. So those are sort of the three most typical forms of chlorine that we're going to use for the disinfection process, which sort of leads to the question, why are we using chlorine? And the main reason is that it's a really strong germicide. It's got high germicidal powers. It inactivates a really high proportion of the microorganisms that we talked about in the earlier slides at relatively low dosages. It's also really soluble in water, which is kind of important because we want to mix it with the water and have it dissolve and react quickly. It's also typically cheaper than a lot of the other methods that are available. It's typically also readily available to purchase in a variety of forms. And the nice thing about chlorine is at the end of the process, you can have a remaining chlorine residual that you can measure to evaluate its effectiveness and make sure that it did its job. That being said, despite all of these advantages, there are some significant disadvantages as well. The main one being that chlorine is toxic to aquatic life. So it requires dechlorination. So if you're putting chlorine in to the stream in order to disinfect before you release the water back out into nature, you have to deal with the chlorine. You have to dechlorinate, and we'll talk about that process in a little bit as well. Also, if it sticks around long enough, you can have it form toxic byproducts like TTHMs and HAA5. This is more of an issue in the drinking water side of things, where we purposefully leave a chlorine residual in the water to make sure that it stays disinfected as it travels through the network. In wastewater systems, they can form, but it's typically a little bit less of an issue because we are looking for shorter retention times. The idea is to have just enough chlorine to do the job so that you can get it out and not to have an excess that's going to be sitting in the effluent. But as we'll see when we talked about the things that can potentially negatively impact disinfection, if you've got high BOD, if you've got high suspended solids, you might actually need quite a bit of chlorine to do the job. So now we talked about the, why and what do we use. Let's talk a little bit about the chemical processes. For the level 1 and level 2 exams, you're not going to need to know typically like intense chemistry, but you should have some basic terms on, as part of your understanding. Chlorine is an oxidant. Basically the process it goes through is oxidation. And basically what that means, remember from chemistry. We've got electrons spinning around the outside of atoms. And basically, under the right circumstances, what it does is it steals electrons from the cells or viruses, and that theft of the electrons is essentially what makes them inert. It basically, again, doesn't necessarily kill them, but it makes it so they can't function properly anymore or reproduce. That being said, I mentioned there are factors that can affect disinfection positively or negatively. Two that sort of affect it negatively are suspended solids and VOD. Essentially, if you've got a lot of stuff in the water, the chlorine has a difficult time getting to and reacting with the microorganisms that you're trying to target, because chlorine is pretty reactive and it will react with other compounds in the water. So if you've got a lot of suspended solids in there, you're going to have the chlorine reacting with them as well. This is actually an issue with other forms of dechlorination or chlorination, disinfection as well, like UV light, right? If you've got murky water, the UV light doesn't penetrate and you'll get disinfection at the surface, but not in the bottom. So a little preview of next section. Because suspended solids and BOD stuff in the water, to put it in basic terms, has this negative effect, we always do the disinfection after primary treatment, right? We settle out the bulk of our solids, we go through our clarification processes so that the water or the effluent that we're disinfecting is as clear as we can possibly make it before we discharge it out. So the idea is, it looks good coming out of clarification, and then we make it safe by doing the disinfection. Other things that can affect disinfection are things like the pH of the water. So remember, pH scale 0 or 1 to 14. Low numbers mean it's acidic, high numbers mean it's basic. Right in the middle, neutral is sort of water with nothing in it. When chlorine comes into contact with water, a couple of reactions take place. The chlorine reacts with the water to form hypochlorous acid. And that then has a second reaction where it breaks into hydrogen ions and hypochlorite ions. And ideally, you want to minimize that second reaction, the one that's listed in the middle on the bottom, because hypochlorous acid, the HOCl that's in red, is the most effective version of disinfectant here. They'll both disinfect, but the hypochlorous acid, the HOCl, that's what we're going for, because it's anywhere from 100 to 300 times more effective than the hydrochloric acid, the hypochlorite ions. And what's going on with the pH is really, really important, because how much of each of these compounds you get is highly dependent on the pH of the water that you're working in. So this graph on the right-hand side shows pH from 0 to 10, and you can see that if we start on the left-hand side, we've basically got all chlorine gas that we're sticking into the water. And the higher the pH is, the more of that starts to turn into HOCl. But if you get over a pH of about 7.5, you start getting the hypochlorite ions, the OCl negative, which don't do as good of a job, which is why in many wastewater treatment facilities, we have pH controls to make sure that the effluent that we're treating stays in a pH range where we can basically do the most amount of disinfection with the least amount of chlorine. So a lot to absorb right there, but things to think about is you don't want a lot of stuff in the water. Ideally, sort of this low to middle pH range is where you want to be, and you want to sort of commit to memory that the hypochlorous acid, the HOCl, is the more effective disinfectant of the two byproducts of chlorine. So with that, I just gave you the answer to this question, but Blair, if you wouldn't mind throwing up question number 2. Got a couple of situations listed here, and in which of these do you think is going to be the most effective for disinfection? low TSS, low pH, and more HOCl, high TSS, low pH, and more HOCl, or low TSS, high pH, more OCl, or high TSS, high pH, more OCl. Remember what we talked about. The idea is less stuff in the water, more of one kind of ion than the other. And think about where the pH scale showed up, or where the HOCl showed up on that pH scale. All right, let's give this about another 15 seconds. All right, go ahead and end the poll and show the results, Larry. Right, so our correct answer here is A. We want low suspended solids, right? The more stuff there is in the water, the harder the chlorine has to work. Ideally, you want a lower pH and more HOCl, so the hypochlorous acid. So just let me go back to that image we're looking at here. And I probably could have worded that question a little better and said lower pH instead of low. But, we're looking for, pH somewhere between 4 and 7.5 is where you're going to get mostly hypochlorous acid. So of the options that we're giving you, and this is actually a good thing to point out, for the operator exams, sometimes none of the answers are exactly perfect, and you have to pick the one that's sort of the most right. So of our options here, low suspended solids, more hypochlorous acid, and a lower pH is going to be the best of the situations that we listed there. So let's talk about some more things that can affect disinfection. Nitrogen compounds in the water, if they're present, then the HOCl will actually combine with them and form chloramines. So, and this is good because it can be measured as a combined residual, meaning that it's combined with hydrogen. You might be familiar from testing with the sort of two different DPD reagents for free and total chlorine. Free chlorine measures the hypochlorous acid and the hypochlorite ion, which are sort of the two effective disinfectant units that we've talked about, whereas total chlorine measures both of those plus anything that the chlorine else has anything else that the chlorine has joined with, like nitrogen compounds. So if you want to figure out the amount of free chlorine, the amount of combined chlorine, or the amount of chlorine that's going to react with the nitrogen, if you do those two tests, you can just essentially subtract the free chlorine from the total chlorine, and what's left will tell you how much of that chlorine is actually reacted with nitrogen compounds. Again, free chlorine is better at disinfecting than combined chlorine. And combined chlorine doesn't degrade as quickly either. So again, we're trying to sort of avoid having a lot of this there. So sometimes, again, drinking water systems deliberately use chloramines because they stay in the system longer, and we want that residual, but that's really not that desirable in wastewater because the chlorine that we put in, we're going to have to get back out. The kinds of nitrogen compounds that might react with chlorine in your system: inorganic ammonia, organic proteins, and amino acids. Again, and these chloramines are called combined chlorine residuals. And again, it is available for disinfection, but it's just not as effective as a disinfectant. And again, it does not degrade in the system as efficiently. There's a concept known as breakpoint chlorination that is good to understand. I'm going to give you a very, very brief primer here. This basically shows on the x-axis the amount of chlorine we've added to a given amount of wastewater effluent in parts per million. And what is shown on the y-axis is the total chlorine residual. We're starting at the bottom left corner at 0, assuming that there's some amount of ammonia or nitrogen compounds in the water. And in this sort of initial upward trending part of the graph, chloramines are being formed. So you're getting that combined chlorine residual, creating those chloramines. And you'll notice it's not in a 1-to-1 ratio, right? It's not a 45-degree angle. It's a slow slope. So if you kind of look over here where the arrow is pointing, we've got about 1 part per million in chlorine, but we have less than 1 part per million chloramines. So slope's a little flat. But as a certain point, as we add more and more chlorine, we get to this point where the graph turns the other direction, and chloramines are being actually destroyed. So the reaction with the ammonium is sort of nearing completion. And then that gets to sort of this dip, this bottom point, which is called the break point. At this point, basically, all of the ammonium has been used up in the reaction, and any other additional chlorine that gets added results in free chlorine residuals being produced. So this is sort of where that free chlorine residual, that effective disinfectant, shows up on the graph. Again, you're probably not going to have to do any math related to this on a level 1 exam, but you are going to have to, be able to identify sort of where the break point is and what's going on. So again, this is an example graph. Any graph from your site might look a little bit different. It's going to all depend on some of the amount of ammonium that's present. The more of that there is, the longer it takes to get to that break point, or more accurately, the more chlorine you need to get there. Another important factor, temperature. Higher the temperature, the quicker all pretty much chemical reactions work. So the higher the temperature of the water, the quicker that the chlorine is going to react with the organisms and particles in the water. It's just, if you think about, when you brew tea, right? If you brew tea with cold water, the tea infuses very, very slowly. If you use hot water, it works faster. It's not exactly a perfect metaphor, but it kind of gets you the idea that the warmer the temperature is, typically the faster chemical reactions happen. Other things that can impact disinfection are things like, concentration and time. So the concentration of chlorine and the amount of contact time that chlorine has with the wastewater that it's treating. Which is why we often see, disinfection races as these sort of long snakes where the water is moving relatively slowly. The idea is you want to give the chlorine enough time to mix with the water and enough time to contact those microorganisms to do the disinfection that it needs. It's important to note that the chlorine concentration and the time it needs to disinfect are inversely proportional or inversely related, meaning that if you have a high concentration of chlorine, you don't need as much time for it to do its job and react. Alternately, if you've got a long contact time, you typically will need less chlorine or a lower concentration of chlorine to do the job. So again, sort of many ways to skin a cat. Your plant will be designed for a specific amount of chlorine and a specific contact time under specific conditions. So again, that's a really important thing to understand. So again, the higher the concentration of chlorine, the less time you need. The more time you have, the lower concentration you need. So we've talked about a couple of things that impact disinfection, mostly negatively, but some positively. Here's a quick and easy question for you. Which of these factors that are listed doesn't affect disinfection? Blair, if you can throw up number 3. So the amount of stuff in the water, so suspended solids, chlorine dosage, quantity of hydrogen ions in it, or operator certification level. All right, we're getting 100% on this one. I think we can go ahead and end this poll. Yeah, operator certification level, right? obviously you want to be certified. You definitely want to be appropriately trained if you're going to be handling any of these chlorine compounds. But whether you're a level 1, 2, 3, or 4 is not going to actually infect the disinfection process unless, I guess, you do it completely wrong, which if you're trained, you won't. All right, so a lot about chlorination, different ways of dealing with it chemically. Let's talk about what comes next. So we've disinfected the water, we've gotten all the solids out, we've clarified it, we've disinfected. Is the water ready to be discharged into the environment? A little bit of a rhetorical question. I think you know the answer. Not if you use chlorine, right? Chlorine is a dangerous chemical. It's toxic, as we mentioned before. So it's really important that we either get it out or neutralize it before we release that effluent in the wild. Typical residuals after disinfection at a wastewater treatment plant could be as high as 12 milligrams per liter. So, 12 parts per million. And fish, for example, can only tolerate 0.01 milligrams per liter. So several order of magnitudes lower. So, if we have chlorination as our disinfection method and we discharge without dechlorination, there's going to be fish kills, there's going to be a lot of negative impacts, and there's going to be fines that go with that. So we want to make sure that we understand the dechlorination process and that we do it correctly. So what is dechlorination? It's just the process of removing that chlorine residual from water before it's returned to the environment. And again, it's because it's toxic. And it will also, again, combine with organic matter to create those chlorinated compounds that can be carcinogenic and toxic to aquatic life and humans. Basically, it's the same problem that you potentially have in stagnant drinking water pipes, those chlorine byproducts being created over time. The same thing can happen in the wild. So there's a lot of different options you have for dechlorination, not all of which are practical, but sort of in theory, just detention for long enough will allow the chlorine to dissipate. If you have the ability to have really long detention times. Aeration can be used. Sometimes in a long contact basin, they'll have aerators at the end, and the aerators will actually effectively mix with the chlorine that's residual that's left and help it dissipate into the atmosphere. Sunlight will actually do it. If you leave chlorinated water out for long enough, the sun will do its job, and that chlorine will dissipate or turn into other compounds. The two typical ways that you see in wastewater treatment plants, though, are activated carbon and some sort of chemical reaction, because typically wastewater plants are sort of size restricted. We don't have an unlimited space to have giant pools of standing effluent to let nature take its course. We usually have to help nature along. So we can use activated carbon, where we essentially let the chlorine adsorb onto the carbon. Activated carbon has lots and lots of tiny, tiny holes. Or we can use a chemical reaction, and sulfur dioxide gas is kind of the most typical version that we use. One of the reasons that it's used is because it reacts almost instantaneously with chlorine, and it also does so in a 1-to-1 ratio. So more or less, concentration of 1 milligram per liter of sulfur dioxide will remove about 1 milligram per liter of chlorine residual. So it makes the math a little bit easier. But there are other chemicals that are used in this process. Things like sodium sulfite, sodium metabisulfite, sodium bisulfite, thiosulfite, calcium thiosulfate. All of these will do the trick. But again, sulfur dioxide gas is the one that's, I think, most frequently used. But just like with the sort of inactivation of microbes where we're not necessarily killing them, the idea here is that one way to dechlorinate is to get the chlorine gas to sort of dissipate out in the environment. The other idea is to essentially turn that, disinfecting active chlorine, the toxic version, into something else, because there are a lot of compounds that have chlorine in them that are non-toxic, like table salt, for example. That's sodium chloride. Um, so which of these you're going to use is obviously going to be dependent on the equipment and the system that your plant has designed. But what we're typically doing in these sulfonation type chemical reactions is essentially converting chlorine from its toxic oxidizing forms, so that free chlorine like the HOCl and OCl minus, or combined chlorine like chloramines, and turning them into ions, chloride ions, which are the same harmless form of chloride that's naturally present in water and table salt. So we're turning it into something that's safe. Sulfur dioxide turns into sulfuric acid or sulfur sulfate, but it's at such a dilute concentration that it's not really going to impact the water pH or the water quality. That's not dangerous for, that end product isn't dangerous for nature. So as a practical result, the chlorine kind of disappears as a toxic disinfectant, and it becomes an inert chloride that doesn't pose a threat to aquatic life. So that wastewater can then be safely discharged. The process, particularly when you're using sulfur dioxide, it's really, really fast and it's really, really efficient. So it's, again, one of the sort of most common dechlorination agents being used. That being said, sulfur dioxide is hazardous. We'll go into this a little bit more in the safety part, but I do want to point out it's a colorless gas. It has a pungent odor, and given enough of it, it can hurt or kill you. So like chlorine gas, like the solid and liquid forms of chlorine that are used for disinfection, do not handle this stuff unless you're trained to do so and authorized to do so. The precautions for sulfur dioxide are very similar to the ones that we're going to talk about for chlorine. But like chlorine gas, this stuff is dangerous. You never want to work alone around this, because if something happens and you're overcome, there won't be anybody to rescue you. The other sort of commonly used dechlorination process is activated carbon. And this is sort of the same kind of carbon filter that you use to get odor and organic compounds out of drinking water, similar to what you might have in your refrigerator. And basically it works because activated carbon has lots and lots of voids on it. And the chlorine will basically attach itself to the activated carbon and pull itself out. There's two different versions, basically. There's powdered activated carbon and granular activated carbon. These are typically a little more expensive than doing the sulfonation processes that we talked about in the last couple of slides. But these actually pull that chlorine out of the water entirely. Downside of activated carbon, whether it's PAC or GAC, is that after a certain point, there's no more space for chlorine, and you have to change the media. So there are costs associated with both of these. The carbon processes are typically more expensive. So I got another question for you. It's more of just a poll. If you do dechlorinate, what do you currently use? Do you use sulfur dioxide? Do you use one of the other sulfites? Sodium sulfite, metasulfite, bisulfite. Do you use carbon, or maybe you don't dechlorinate, or it's not applicable, or you're not sure? And that's the thing, if you don't chlorinate, you don't have to dechlorinate. So for example, if you've got a UV disinfection system, this isn't going to be relevant to your particular operation, although of course it's going to be relevant to the exam, because again, even if it's not a typical process in your jurisdiction, you still need to know about it for the exam. So all right. Why don't you go ahead and share the results? Okay, yeah. So yeah, it looks like we're using the non-gas versions, and it sounded like there wasn't much chlorine gas used in the islands either, and that's probably due to logistics, but that's actually kind of nice to know, because those other compounds are typically a little bit safer to use and pose less danger. All right. So got one more question for you. Actually, I've got two more questions for you. So why do we dechlorinate? got a couple of different options here. Because of its smell, because of the discharge permit requirements, because it's harmful, or maybe both of those last two. All right, give it about another 10 seconds. All right, go ahead and end the poll, show the results. Right, so the answer is B and C. So if you happened to pick chlorine as harmful in the environment, you weren't wrong, you were only half right. But yeah, it's typically a requirement of the discharge permit, and it's a requirement because it's harmful. All right, here's a little more hard question. Number 6, which of the compounds that's listed here actually will not work for dechlorination? And this is also a kind of exam question that you might run into on an exam. So we've got sodium thiosulfate, we've got PAC, powdered activated carbon, we've got sulfur dioxide, and we have caustic soda. And this again is one of those things where you might have to memorize it, but if you've got a good understanding of the processes that are used in wastewater treatment in different stages, you should be able to sort of logic your way through here. So again, the question is, which of these is not going to work for dechlorination? There's 3 that work for dechlorination. There's 1 that doesn't. All right, let's go ahead and end the poll in 5 seconds or so. Yeah, so the correct answer here is caustic soda, which is, again, one of those questions that might throw you for a loop because caustic soda is definitely used in wastewater treatment. And as we'll see, it's actually used for chlorine scrubbers, which are part of the safety equipment, but it's not actually used for effluent dechlorination. So sodium thiosulfate, sulfur dioxide, and PAC are all potential options for dechlorination, but caustic soda is not going to do the trick. So in this case, again, and this is one of those things with the sneaky exam writers, you got to read closely. This is which one will not work. So caustic soda is our answer for that one, but caustic soda, again, is used to raise pH, which we might do to get ourselves into that sweet spot so that our chlorination is more effective if we happen to have low pH wastewater for some reason. And again, as we'll see, it can be used in chlorine scrubbers, which are part of the safety equipment. All righty, let's see, we'll end that. Which brings us to safety. So just in general, a lot of the chemicals that are used in wastewater treatment are potentially very, very dangerous. So it is really important that the safety data sheets associated with the chemicals that you are using are available and that you read them so that you know what to do if you are exposed to them. The last thing you want to do is be exposed to a dangerous chemical and then have to go figure out what it is you want to do. These are the kinds of things that, if you work with chlorine, if you work with sulfur dioxide, you should memorize the safety data sheet. You should understand the safety data squares and the hazard communication pictograms, because these are going to be on all of those chemicals. So in the safety data sheet is going to give you a rundown of, what it is, what's dangerous about it, what to do when you are exposed to it. The safety square is going to basically list health hazard, fire hazard, reactivity, and a specific hazard. So is something an oxidizer? Is it radioactive? Is it corrosive? And within the other factors on a scale. being able to sort of look at those and realize that, like, hey, this is a deadly chemical that might detonate is really useful. You don't want to be making unwise decisions because you didn't read. And again, those OSHA pictograms are really, really useful because they'll typically be on the outsides of chemicals. So you will know whether something is, for example, down at the bottom left, acute toxicity, which means like basic exposure can kill you. Or whether it's an oxidizer or something that shouldn't go into the environment. So those often show up on the exam as well. Make sure that you understand them, but more importantly, make sure you understand how to read these safety tools so that when you're evaluating the chemicals that you're working with, you make sure you do those safely. Even though none of you seem to use actual chlorine gas in your operations, it is a favorite of exam testers everywhere. So I want to give you some basics about chlorine just so you understand. And again, you may move to a different job, to a different plant that actually does chlorine gas. So a little bit about chlorine. It's greenish yellow. That's actually a picture of some in a vial there. It is 2.5 times heavier than air, which means if it's exposed, if you have a leak in a tank, it's going to immediately sink to the floor. Unlike in a fire situation where they tell you, oh, there's smoke in the room, get close to the floor and scurry out to avoid the smoke. If you do that with chlorine, you're liable to kill yourself because the floor is where all the chlorine is going to be. When in doubt, keep your head up and get out. Chlorine gas turns into hydrochloric acid when it comes into contact with moisture, like in your lungs or your mouth or your eyes. This is what makes it so deadly. It turns it into, one of the strongest acids around when it comes into contact with you, and it does damage very, very quickly. If you are a fan of, History Channel, you probably know that chlorine gas was used in World War I to kill soldiers. It is a very effective at killing people, so you do not want to mess around with this stuff. It also decreases the pH of water. It doesn't support combustion, which is one of the few good things about it. And as I said, it's going to typically come to you in a liquid form in pressurized cylinders, typically 100 to 150 pounds. You may have 1-ton cylinders if you're a larger facility. And there are rail cars that have 16 to 90 tons of these. Typically, those cylinders are going to be filled about 85% full. And again, chlorine is only a liquid at high pressure. At room temperature, it will turn to gas. So how to know if you're exposed to chlorine? Number one, you will be able to smell it. It has got a really distinct smell. But blurred vision, watery eyes, burning sensation in your nose, throat, or eyes, coughing, tight chest, difficulty breathing, nausea and vomiting. If you're in an area where you know there's chlorine and you start to feel these kind of things, get out. Chlorination systems typically look something like this. You've got a cylinder that has liquid chlorine in the bottom, chlorine gas at the top. There's a regulator valve that'll typically feed through a rotometer so that you can tell what the dosage is. There's a regulator, which may be automated or manual, or a combination of the two, that regulates the flow. And then that chlorine gas goes into the pipe through an injector, or sometimes it's called an ejector. This is what they typically look like out in the field. And you'll notice some specifics here. We've got these tanks all capped with their hazard labels on them so that skull and crossbones, exposure one time in a big enough dose could kill you. It's an inhalation hazard. The caps are on there so that if something falls over, we don't actually knock the cap off and have a leak. You'll notice that there are safety signs all over the place. And instructions. You can see on the wall to the left there, scales that tell you how much chlorine is left in the cylinder. And sort of looking up close, what we've got in the middle there is the regulator. The rotometer is on the right-hand side, and then the scale is up there in the left-hand corner. And notice this, there's a wrench attached there so that if there's a leak, it can be cut quickly. The last thing you want to do is discover a leak and realize you don't know where the wrench is. Most of these systems, probably all actually, will have a scale to let you know how much chlorine is left in the tank. These particular scales are set up for 150-pound or 100-pound tanks. You'll notice down at the bottom on the scale, you see the 150. When the tank is full, that's where the needle would point. When it's empty, it would point there. And right now, where the needle is pointing, you've got about 11.5 pounds or 12 pounds of chlorine left in that tank. So it's really important to be able to understand how to read these meters as well. And then I talked about the chlorine injector, or sometimes called ejector. It's essentially going to be a fixed apparatus that has a gas injector that basically shoots the chlorine gas into the stream of effluent. Systems might also look like this. This is a bigger one, but you can see all the same components. They just look a little bit different. The one thing about chlorine tanks is they all have fusible plugs as a safety device. I noted that they're filled to about 85% full. If chlorine tank gets too hot, it will explode. The tank will rupture. And so to prevent that from happening catastrophically, all chlorine tanks have a fusible plug in them, which will essentially melt somewhere around 157 to 160 degrees. And the idea there is if it gets really, really hot, it'll release gas to prevent the buildup of explosive pressure and the possibility of a catastrophic rupture. It's kind of the lesser of two evils. Ideally, we don't want chlorine gas escaping into the environment, but if there's a fire, it's better to have the chlorine gas escape and get burned than to have the tank explode. How many tank plugs you have on a tank is going to vary. 100-pound and 150-pound cylinders have a single plug. The ton cylinders actually have 6 of them because, again, there's more volume to vent. Which brings me to a very critical safety point, which is that you don't want space heaters anywhere near your chlorine tanks. So this is a sign from a place that we visited that basically says why you don't want this. A space heater 12 to 24 inches away from a cylinder can allow the cylinder to build up enough heat to actually melt that plug and cause an accidental discharge. And as they put it in here, actual experiments done unintentionally by numerous chlorine users across the nation have proved the calculations correct by melting the fuse plug and releasing the chlorine. Again, this stuff is really, really dangerous. People die, unfortunately, with some regularity because they don't follow safety instructions. So if you are ever working around chlorine, make sure that you follow all the rules and SOPs around it, like keeping it safe. You'll notice they're always chained to the wall. They're typically in a separate room. Extra tanks are stored in a separate room from the ones that are being actively used. You keep it away from gasoline and other organics, and you bring it into the room when you need a new tank. You don't sort of store everything haphazardly, and you make sure that they are chained up. So protect it from the elements, protect it from heat, and protect it from things like gasoline and other things. Any chlorine gas room has to have a very specially built ventilation system. You want to have a light switch and a vent switch, typically outside the chlorine room. You want to have fresh air intakes up high because, as I mentioned, chlorine sinks to the ground. So you want fresh air to be able to come in. And if you look at that picture on the bottom right-hand side, you'll see that one of the pipes actually goes down almost to the ground. That's the air discharge pipe. So we've got fresh air being discharged within about 12 inches of the floor, and then we've got something very close to the floor that will suck the chlorine contaminated air out and send it off to a treatment system, which is typically a chlorine vapor scrubber, which, as I mentioned, might be built with caustic soda, which has its own safety concerns. Again, you don't want to ventilate chlorine gas out of the building and into the wild. So the idea is that if there is a leak in the room, you get out, you close the door, you let the chlorine scrubber do what it needs to do. This is a typical chlorine setup where you've got a storage room. That's the first room on the far left. You'll notice the vents are all up on the ceiling. So there's a vent in the storage room. There's a vent in the actual chlorine dispensing room. You'll note that at the floor there, you've got a vent over to the scrubber. So that'll handle any leaks that are in there. And then nearby, but outside of that entire area, you've got your scuba air packs, so that if somebody needs to go in and deal with it, they can have the appropriate equipment at hand. And there's also a shower and an eye wash. And most importantly, an emergency power setup. You don't want to have a chlorine room that can get knocked out of function with a power outage. So you got to have emergency backup power available. So if there's an accident during a power outage, the chlorine scrubber can do its job and keep us all safe. Biggest part about chlorine safety is that you want to have a team that's trained to deal with leaks and use proper equipment and procedures. You got to have a self-contained breathing apparatus located near the door outside the chlorination room. Got to have a treatment system that's going to deal with contaminated air. You got to have an alarm system so that people know. And again, you need that standby power source for operating the chlorine ventilation, the detection system, and the air treatment system. A little bit about chlorine gas safety. I know we're running out of time here. I'm going to end up going over a couple of minutes. You can check for small leaks safely with an ammonia solution in a squeeze bottle or with a rag or a paintbrush, but not a spray bottle. So if you were to take a squeeze bottle like the one shown up there with a 30% ammonia solution and dribble it on a suspected chlorine gas leak, it would create white fumes. The reason you don't want to use a spray bottle is spray bottles atomize into the air. And if there's a lot of chlorine present or a little bit of chlorine present, it might turn the whole room white. So you want to be very sort of close and directed. You'll see white fumes. If that happens, get the heck out the door. If you can turn the chlorine valve off, great. But if the choice is spending more time in a contaminated area or not, the best thing is to go out of the room, get appropriately suited up, or call in the folks who are trained to do that. It's really important to find leaks and repair them quickly, but you have to take the equipment out of service to repair it. Chlorine leaks are not the kind of thing that you can repair while they're under work. So there's a whole process around this, but basically you're going to want to shut off the chlorine supply. You're going to want to evacuate the lines and then turn off the water, because anything that's left in the lines is going to vent out into the air, which is going to, again, cause the problems. Most important thing, limit exposure. Again, only authorized and trained personnel should be anywhere near chlorine gas. You want to have clear visible signs. You want to have trainings. As I mentioned, chlorine has a smell, which fortunately we've got really good noses at 0.2 parts per million. There's a noticeable odor. If you smell that, leave. But just note, like 15 parts per million is going to cause serious irritation in your eyes after a couple of minutes. 30 parts per million, you'll start coughing. If it's 1,000 parts per million, you'll be dead in a couple of minutes, which is, again, why it's best when there's a leak to leave, assess, get suited up, and deal with it. Just in the 10-year period, 2001 to 2011, 14 people died from on-the-job chlorine exposure. So we don't want you to be a statistic. We want you to be safe with this stuff. As I mentioned, sulfur dioxide gas, which again, most of you aren't using, is also hazardous, although maybe not quite as hazardous as chlorine gas, but it's also got a pungent smell. It can kill you. It's colorless, so you will not see it, but like chlorine, it's heavier than air. So sort of the similar precautions that you use for chlorine apply to sulfur dioxide. It also forms acid in the presence of moisture. Again, think eyes, nose, lungs, not something you want. You don't want to handle it unless you're trained or authorized. And you never want to work alone with either chlorine or sulfur dioxide, because again, most things that are dangerous, you do it in pairs so that if something goes wrong, there's somebody to help you. I'm going to skip over this, but you can read this at your leisure. It's basically just sort of the effects of sulfur dioxide gas. You notice that 400 to 500 parts per million, it's dangerous. And there are documented cases of fatalities caused by sulfur dioxide too. So again, we don't want you to be a statistic. Hypochlorites also have some safety issues that you want to be concerned about. So these are the liquid sodium hypochlorite and solid calcium hypochlorite. They're not really flammable in the sense that they won't burn when exposed to a match, but they can react explosively. They're corrosive. You don't want to keep them anywhere near compounds like ammonia and amines and organics, which is why, again, there are safety procedures and storage procedures. And the downside of hypochlorites is you may not smell hazardous concentrations like you would with chlorine gas. And they are toxic by skin or mouth. So again, PPE is critical. You want to make sure you know what you're doing and you've been appropriately trained before you start messing with this stuff. Hypochlorite, ideally, you're going to store it around 60 degrees away from acids and ammonia that it can react with. You know, you probably remember from home ec class, you really don't want ammonia and bleach coming together. That does not work out well for anybody. It's typically stored in, you know, airtight bottles or drums, and we keep it away from sunlight because sunlight will degrade it. Again, calcium hypochlorite, it's the powdered form. It's also dangerous. It's an eye irritant, nose irritant, a lung irritant. You don't want to be around this stuff. It is extremely corrosive when wet, which is kind of funny because we're mixing it with water to do its job. But it can actually be explosive at temperatures over 100 degrees. So you have to, again, follow the appropriate safety precautions with these. You really only want to mix it with water using corrosion-resistant materials. You're going to minimize dust. You do not want to be eating, drinking, smoking, chewing gum, or doing anything else when you're handling chlorine in any form. Use the PPE that's appropriate. If you get solution or dry chemicals on your skin, immediately flush with large amounts of water. If you are working with these, it is really, really important that you know where the showers and eye baths or eye wash stations are, so that, you know, if you get some of this stuff on yourself accidentally, you can get it off as quickly as possible. And last but not least, when you are mixing these, you put the powder into the water, not the other way around. If you had a jar of calcium hypochlorite and pour water into it, you're liable to trigger an explosion. Whereas if you have a large volume of water and a small volume of calcium hypochlorite and you mix it the other way, so powder into water, it's not going to be as dangerous. Again, sort of typical things that you would think, you know, keep it in a cool, dry place, label your containers, keep it away from those organic chemicals. And one of the last things that I'm going to show you is why you want to keep this stuff away from organic chemicals and pesticides. This is almost real time. It's sped up very, very slightly. But this is calcium hypochlorite and DOT3 brake fluid, which by themselves are basically inert and don't do anything. But you mix them together and wait about 30 seconds and you will get fire. So you can already see it's starting to smoke. And within about 30 seconds, we've got a full-blown fire here. So again, you really want to be careful with this. Do not try this at home. One of my coworkers did this with the appropriate PPE. You know, you see videos like this on YouTube. Don't do this at home. It's dangerous. The byproducts are nasty. But I'm showing you this to make a point that you want to treat this stuff carefully because it can really, really hurt you. Dechlorination tools, like I said, sulfur dioxide. It's also got issues around it. Basically handle it like you would with chlorine. You know, it's colorless, it's odorless. I mean, it has a pungent odor though, but it is a compressed gas. It can cause burns. Again, make sure you understand the safety triangle. Make sure you read the safety data sheets that are associated with it, because they will cue you in on what to do, what not to do, and what to do in the case of an accident. So I realized that was yet another one of my sort of fire hose of information presentations. I apologize for running over, but I think this content, particularly the safety stuff, is really, really important because it is often a focus of operator exams. And again, we want you to be safe in your job, in your career, and not end up as a statistic. So that's why we kind of harp on or emphasize the safety aspects. So with that, again, thanks for attending. Thank you for being part of this series. Thank you for getting into this field and helping keeping your community safe. And thanks for getting a better understanding of chlorination and dechlorination, so that we can keep our fishy friends safe. And with that, I will open the floor to any questions that there are to see if I can answer them. And I will put our contact information up. Again, this is one of those things where if you don't have a question off the top of your head at the moment, but you come up with one later, you can always shoot us an email, and we're happy to answer whatever questions you have for us. So again, thanks for coming. This was Disinfection 1. In 2 weeks, AJ is going to come and talk about some of the other sort of high-tech ways that we disinfect using UV and other methods. I think that's going to be a really good session. AJ is a level 4 operator who worked at the Albuquerque treatment plant for years, so he's got a real lot of practical experience and knows his stuff inside and out. So again, if you have any questions from this session that you don't get to, you can always ask them in the next one. I'm sure AJ will be able to answer them as well. So thanks for attending. Again, sorry for keeping you over. We'll have the recording up within the next day or so and the slides. Again, feel free to reach out. Thanks for joining us. And if there are no further questions, I will give you back the rest of your day.